So I hope you enjoyed that video on electric vehicles. I wanted to show you one more map of electric vehicles and their impact of their charging on the grid with respect to emissions from that charging. So I alluded to this before, where depending on where you live and where your electricity comes from will impact the associated emissions from your electric vehicle. So here's a great map of the United States, and there's some specific numbers here in terms of where the best places are to charge electric vehicles. And if you see, the dark blue, medium blue, and light blue correspond to the good, better, and best of how do the global warming emissions of electric vehicles compare with gasoline vehicles in your region. And also, more quantitatively, an electric vehicle charged in the given region produces emissions equivalent to a gasoline vehicle with a fuel economy rating of. And the three different categories of good, better, and best correspond to, as shown, 31 to 40 miles per gallon versus 41 to 50 miles per gallon versus greater than 50 miles per gallon. And so we see here that there are regions in the country where actually having a gasoline vehicle is might actually be better depending on what kind of vehicle you're driving and what kind of efficiency you have. In the state of Ohio, for example, depending on how much you drive and whether or not you're driving on highways or whether or not you're driving in the cities, that matters as well. But a hybrid vehicle might be less polluting than a pure electric vehicle. So because of the mixture of gasoline and electricity from the coal-burning power plants. Now, of course, again, if you get your electricity for your electric vehicle straight from a solar panel, it's a whole different argument altogether. So the transportation sector is undergoing a lot of innovation and has been over decades, and that innovation may be focused on reducing emissions. There are these standards that were put in place called the CAFE standards, or the Corporate Average Fuel Economy Standards. They're set for 2011 through 2020, so that by 2020, the average car is at 35 miles per gallon. So that's 40% higher than what it was in 2010. So these are pretty stringent standards that are being put in place that the car manufacturers need to meet. And how are they meeting these standards? Well, they're producing lighter vehicles, so they're using plastic composites, aluminum instead of heavy metals often. This leads to a 10% reduction in vehicle weight. And as you would imagine, it takes more energy to move a more massive object. So a reduction of 10% in vehicle weight equates to a fuel consumption reduction of 5 to 7%. So that's pretty significant if they can do it. Of course, there's improvements in energy efficiency per vehicle mile. Some of that comes from being able to burn the fuel cleaner, more efficiently in the actual combustion engine. And over the past decade, we've seen relatively small, but still enough to make a difference, improvements in efficiency of about 1% per year. And these, in addition to the improvements in the actual engine itself, we can also improve the energy efficiency other ways by streamlining the car. So essentially reducing the drag on the car, because now we have more streamlined versus a boxier car. Actually improvements in the tire to reduce friction loss. Now, we want friction because friction helps us stay sort of glued to the road, and that's important. We don't want the road now all of a sudden to be like an ice rink. So friction is important for safety, but also friction leads to energy not being used efficiently. So some balance between minimizing friction losses but still having enough to account for safety. There have been some improvements with respect to that. We've already talked a lot about hybrids that recoup the braking energy. So instead of just when you put your foot on the brake and all of that energy going straight to heat, it's able to recoup and then store some of the energy in the battery. And then just a better energy management, if you will, of the overall energy use on board that hybrid. Now, also, if we can make sure that electric vehicles are charged by renewables. That's another way to help with our emissions. And then now here's a little bit more details with respect to the engine improvements that I mentioned before. Valve timing, this refers to in a combustion engine, you have to very carefully time when the valves are open and closed, when you're bringing in your air-fuel mixture and when you're exhausting after the combustion process. And getting that timing just right helps with your efficiency. The cylinders inside your engine need to be manufactured in such a way and used in such a way, again, that we have an efficient combustion process. Injecting and turbocharging, lubrication being very important to reduce on frictions, making sure that the pieces and parts in our engines are at the appropriate temperatures where efficiency is maximized. Compression ignition, we're not going to talk too much about internal combustion engines, but those of you who know about the combustion process know how important the compression ignition and the combustion engine overall's efficiency is influenced by having tight control over that type of compression ignition, if applicable. Increasing the number of gears in a transmission system also helps us have a little bit more control over the acceleration of our vehicle, and then any other kinds of loss reduction that we can have in the bearings, in the gears, in the hydraulic system itself, minimizing those losses, sometimes through lubrication, sometimes through insulation, and sometimes through requiring heat exchange in a certain way. So there are lots of parts of the engine where we've seen improvements and will continue to see improvements. Other ways where we'll see reduced emissions due to innovations in the transportation sector come from the decarbonization of the fuel supply. So we've talked a lot about this. I mean, this can be anything from better types of fuels that we're putting in our car that have reduced emissions. We've talked about natural gas versus traditional conventional gasoline having a lower carbon content, but also moving to electric vehicles as long as we're charging those electric vehicles in an efficient way that emissions are low. Also, changes in uses of transportation services, relying more and more on the right kind of public transportation. Smarter cars, right? Congestion causes a lot of emission. So if we had smarter cars that knew other directions to move, other paths to take in a particular on a particular route to get somewhere, to reduce the congestion and traffic jams, that could lead to lower emissions. That gets into this idea of automated highways, maybe even cars that drive themselves and are not sort of human powered, which could lead to the use of higher speeds than necessary, of perhaps not using your engine in the most efficient way. So having more smart integrated into the whole transportation sector would undoubtedly lead to better optimized use of our cars and therefore reduced emissions. Maybe even laws that reduce congestion, such as no more than X amount of cars are allowed on the road during particular times, or certain type of cars allowed on the road during certain times could lead to reduced congestion. And then we've seen a rise in telecommuting, certainly over the last decade or so. And if that trend continues, hopefully we'll see a reduction in emissions as a result. And we've already seen a small one over the last several years. Now, the last thing I wanted to talk about, fuel cells. We haven't really had a chance to talk about fuel cells in this class just yet. And talking about it with respect to the transportation sector makes a lot of sense. Fuel cells typically generate their electricity from the electrochemical reaction of hydrogen and oxygen. There are different types of fuel cells, but the type of fuel cell that's particularly attractive for transportation applications is the proton exchange membrane. And generally, fuel cells exhibit high efficiencies at low powers, but they also provide a wide range of power outputs, so making them particularly suitable for the vehicles. And in a fuel cell, there's typically minor losses, so many fewer parts, if you will, where you can have losses that lead to lower efficiencies. Fuel cells are typically 60% efficient, even above that. And again, you'll see reductions once you take a fuel cell and put it in a real car, but those reductions are not significant. Typically, the best kind of fuel cells are run on pure hydrogen, but the barrier here is that hydrogen must be produced from other fuels or from the electrolysis of water. And the storage of hydrogen is quite difficult. Again, hydrogen is a gas, and so it takes up a lot of space. So you have to worry about space, and in a small car application, that can be difficult. It also requires high pressures, which comes with complications as well as safety concerns. Hydrogen is also flammable, and so again, so is gasoline, but hydrogen flammability is certainly something that's of concern. The present storage systems for hydrogen require about 5% hydrogen per unit of storage system weight. So for every kilogram or gram of hydrogen, right, for every kilogram of storage, we can only store about 5% in terms of kilograms of equivalent of hydrogen. So again, a large storage system is required, but keep in mind the specific energy of hydrogen is about 3 times that of gasoline. But so if you do the math, basically the storage system weight penalty of hydrogen versus gasoline is still a factor of 20. So that's quite a large increase in the weight of that storage system. So for example, a fuel cell that might even have twice the efficiency of a combustion engine might require about 800 watt hours per kilogram of hydrogen. That's about, in terms of the hydrogen storage system. So that's about 4 times the requirement of a gasoline storage system. Maybe similar to what we would expect from a battery, and which is why fuel cells are now being looked at as alternative to batteries, and maybe really are best suited, at least with the technology we have today, in sort of a combination application, a hybrid type application, similar to how we see hybrids today with respect to gasoline and batteries, maybe seeing a gasoline fuel cell or even a gasoline fuel cell battery type combination lead to a reduction in emissions. Another suggestion and technological possibility that's out there is, rather than requiring this large, massive hydrogen storage system, to have some kind of fuel on board, a liquid fuel, from which you can produce hydrogen on demand. So some kind of onboard hydrogen production system. The problem with this is that it's incredibly expensive in addition to its complexity, and really doesn't pose a viable option, at least right now, with respect to the technology. But I think we will see fuel cells entering the vehicle space more and more, certainly over the next decade or two.